Hi guys, welcome back to another video. Today we're going to be solving a very complex problem. Alright, let's get right into it. I'm not going to be wasting any time. Alright, so we have I to the x is equal to a. Very clear. Let's quickly define all of our variables. It's all good practice. I, we know, is equal, I squared can be I squared is equal to -1, and we can extrude the definition of I from this. So if we take square root on both sides, we can kind of say I is equal to the square root of -1, but I did get a comment saying that this is not quite true. Maybe some people are taught it differently, and you can feel free to leave your definition of I in the comments down below. And on the right-hand side, we have a, which is some arbitrary number. X is what we're solving for. We're trying to see if we can find x in terms of I and a. All right. Let's get right into it. And I, of course, is the imaginary number. Okay, so the solution for this is actually really simple. As you know, we can describe numbers in their polar forms, and here's what that means. If I draw a quick graph, I did this in one of my previous videos, but I'll quickly re-explain it. I have a real axis right here, real, and an imaginary axis. I can define any number in the real plane in the real axis or the imaginary axis using this formula, r e to the I theta. And I'll explain what that means. Let's say this number is I, this is 2I, this is 3I, this is 1, this is 2, this is 3. Basically, let's say I want to describe 1. I can describe this by the distance from the origin to 1, which is 1 times e, which is Euler's number, 2.71828. And there's a much more rigorous proof behind this, but I'll be just explaining what it is. And then the exponent is I, and then theta is basically the angle this makes with the real axis. And that's, of course, 0. So 1 is equal to this in polar form. Now, to describe I, which is what we're going to be doing for the purposes of this solution, I right here, we have to get the distance from the origin, which is 1. So we have I is equal to 1 e to the I, and what's theta? Theta is this angle right here. This angle is 90 degrees, aka pi over 2. And for polar form, we use radians, so pi over 2. So I is equal to e to the I pi over 2. Now we can plug this definition back into our original formula to solve for x. So we get now e to the I pi over 2 all to the power of x is equal to a. Now, someone said that I can't multiply exponents because in the complex world, a to the b all to the power of c might not always equal a to the bc. It was a really interesting comment. I left a reply, and I really appreciate those comments because it can sometimes show different flaws or nuanced thinkings about the complex plane, which is really good since it's so obscure in mathematics. But since we're dealing with the principal definition of I in polar form, it's perfectly okay to do this. We're not using different angles. And here's what I mean. I was saying that we can describe any number or anything in this polar form using that angle, theta. But remember, angles, there are infinitely many angles to describe this. And these are called coterminal angles. So in reality, I have to add a plus 2n, I have to do parentheses here, plus 2n pi right here. That's how I would describe this angle. But since we're dealing with the main or principal definition of I, that's what I is. So this, if you're getting a little confused, don't worry. We're just saying that we can multiply exponents right here because this is the basic or principal definition of I. That's all. So now we have, I'll use white, e to the I pi over 2x equals a. Hey, you can see where I'm going with this. Just take ln on both sides, ln. We have cancel. We get I pi over 2 x equals ln of a. And then we get x equals 2 ln a over I pi. I don't like I in the denominator, so we can multiply by I over I, which is just 1. And then we get, ladies and gentlemen, x equals 2I ln a over pi. And since I squared, we get negative. So that's our value for x. But are we done here? I don't think so. Let's take a look. What is I to the power of 1? That's just I. I squared is -1. I cubed is just I times I squared, which is -I. I to the fourth power is just I squared times I squared, which is just -1, times -1, which is 1. And then we have I to the fifth is equal to I to the fourth times I, which we said was 1 times I, which equals I. So you notice a pattern here where the results of raising I to a certain integer exponent began repeating. And we can account for this in our formula. So you'll notice that this is I again, the result matches. Then what's I to the sixth power? Well, that's just going to be I to the fourth times I squared, which is 1 times -1 equals -1. And when you look at that, this matches up. And this, in fact, happens for every time we add 4 to the exponent. So if I take this exponent of 1 and I add a multiple of 4, so I add, you see this, plus 4n, and I add another plus 4n. What's 4? Yeah, plus 4n, n equals 1, n equals 2. But what's 4 plus 5? That's just 9, which means I to the ninth will give the same answer, I. That's the thing. So essentially what we're saying is we were solving the equation I to the x equals a. And since we got a definition for x, we also need to account for the fact that I to the x is equal to I to the x plus 4n, where n is an arbitrary integer. So we have to account for this by simply adding 4n to our solution. Because when we just add any multiple of 4, where n is an integer, of course, in the exponent, the results, they are the same, which we just proved here. Or not proved, but we just showed it by example here. And there is a proof to this, of course. There is a proof to everything. But yeah, if this helps, that means, I missed that one dot. That means, ladies and gentlemen, our answer is x equals, that's not an x. X equals -2I ln a over pi plus 4n. And substituting a value for a will give us a solution to the equation I to the x equals a. So if we substitute pi, we get x equals -2I ln pi over pi plus 4n, where n is an integer. And that means if we take I to the x, where x is this, I'll do that in red, that'll actually give us pi. And if you plug it into Wolfram Alpha, this is correct, which is it's really astounding, really. So if you have any questions in the comments down below, let me know. But real quick, if there's an alternative way to do this, here's a quick other one, which I also like. I'll do it real quick. If we have I to the x equals a, I can just take ln on both sides regardless, and I don't have to substitute for I. ln, I can move this down. I get x ln I equals ln a. And what's ln of I? I think I said this in my other video, but ln of I is equal to ln of -1 to the power of 1/2. We bring exponent down. We get ln of I equals 1 over 2 ln of -1. What is ln of -1? I've said this one multiple times, but e to the I pi equals cosine pi plus I sine of pi by Euler's formula. This becomes 0. We get e to the I pi equals -1. Take ln on both sides, ln, and then we get ln e cancel. ln of -1 equals I pi. So we substitute that back in for there. We get ln of I equals 1 over 2 I pi, which is equal to I pi over 2, just like that. We substitute that back in. I hope you're tracking. You can pause the video if you need. Then we get x times I pi over 2 equals ln a. X is equal to 2 ln a over I pi. I don't like I in the bottom. Multiply by I over I. This becomes -1 on the denominator and then I on the top. So this is equal to -2I ln a over pi, and we add our 4n, where n is an integer because of the rule, because of how I works, the nature of I, and how it repeats every 4. So yeah, we get the same answer actually by doing it in a different method, which is the beauty of mathematics. If you have any questions, let me know in the comments down below. If I made any mistake, let me know as well. So yeah, thank you guys. See ya.